Our project is the social distance sensor. I'm Preston.
I'm Jagger.
Braden.
All right, let's get right into it. So our problem was COVID-19, and to solve this, we designed the social distance sensor. So COVID-19 has caused social distancing rules to be enforced in most public areas, and as it continues to spread, it may not be long until we must be socially distant everywhere. Without tools to help us, it can be hard to know if we're abiding by social distancing guidelines. So the purpose of this project is to assist those who are concerned with following social distancing guidelines. The CDC says that social distancing is especially important for people who are at higher risk for severe illness from COVID. So our product is more targeted towards at-risk people, but that doesn't mean anybody can't use it. We made this design because COVID is a real thing for many people, and it's important to us that those at risk are protected.
Alrighty, so our functional needs of this are it needs to be comfortable, it needs to be simple to use because usually people who are at high risk are either elderly or have some other problems. It has to detect past 6 feet because that's what the CDC requires. It has to be a quick response, otherwise you're gonna have no clue if you're 6 feet away or if you're too close or too far. Um, the simple and easy to use is for the elder, like it says here. And then compact size and lightweight is just so that it's not like interrupting your wrist movements or anything like that. For our specifications, we want to make sure that it's adjustable so that any size wrist will be able to use it. It has to detect past 6 feet because that's what the social distancing guidelines are. Must be easy to use for elderly people. And then if it responds faster, you'll be able to know if you're within 6 feet, and you'll have to be able to see it during the day.
All right, so to meet all those specifications and functional needs, we had to brainstorm some ideas. So the main things we were concerned about brainstorming were measuring distance, alerting the user, being comfortable, and being power efficient. So some of our ideas for measuring distance was use an ultrasonic sensor, infrared sensor, a tape measure, because little tape measure doodad on the wrist would be pretty cool, and a laser that measure distance. And then to alert the user, we were either going to use a red and a green LED light. Red for if you're within 6 feet, green good, so you're outside of 6 feet. 4-bit LED, four-digit display. Uh, Yellow LED to make sure if you're kind of in between like 4 and 6 feet outside, or like a buzz or a beep to alert the user that they're within 6 feet. And then to be comfortable, we kind of had like the adjustable wrist strap or like a glove. And to be power efficient, we thought about maybe making like a crank turn, like those old flashlights, single A battery, double A battery. Thought about making it solar powered, but at the end we kind of decided to just use like a standard 9-volt battery. So then after we kind of brainstormed how we were going to get it done, we had to figure out like what it was going to look like. So here are some images of other brainstorming ideas we found off the internet. And so our main reason of doing this was just kind of put our thoughts into picture, see how we wanted to pull this thing off. And then that leads us to our decision matrix.
So for our decision matrix, we had our criteria of accuracy, easy to read display, power usage, comfort, ease of use, time, durability, and size. And what we came up with was our ultrasonic with LED, LCD, and button, just because it's easier for use and will be more power efficient and everything like that.
All right, so here we have our bill of materials, and we had one of our group members kind of no call, no show this week, so we're going to do our best to cover his slides. So our total cost of our materials was $61.58. Realize that this is a prototype and not like a full-scale model that we'd go out and sell. If it was, we'd probably make it a lot smaller and use more inexpensive components.
All right, for the engineering analysis, we calculated the total power draw with a heavy use case, and it was kind of easy for us to do that. Assuming the user uses the device 7 times an hour for 5 hours a day, you can see how long each part will be on throughout the day. For example, the Arduino will be on for 49 seconds an hour and 245 seconds a day. To calculate the power draw, we looked up the specifications of each part and how much power they drew while on. In the end, with our use case, the device will last around 150 days before the battery needs to be replaced. And that kind of brings us to the code logic. To explain what the code does is easier than explaining how it all works. First, the variables are set for which pins are being used, the numbers that can be displayed, what to do when something goes wrong, how long each signal should take, etc. Then, after everything is declared, the Arduino is told what we'll be using, what pins will be inputs and outputs, resetting everything, how much data to use, and the loop function itself is very simple. It just goes through the mux display and measurement display machine functions, which is the functions that are named, for basically wait for the button to be pressed and all that. The code waits for an input from the button, and once the button is pressed, the ultrasonic sensor is told to send out a sound for 10 milliseconds, and then the code takes the output from the sensor and converts it into feet and inches. Once that has happened, the display is told which numbers to display, and a green LED lights up if the feet measured is 6 or greater, and if not, then the red LED will light up. The display and LED will be on for 3 seconds before turning off and re-entering the cycle.
So our other partner was supposed to do the 3D model, but he was not able to get to it because he was gone. So we have our diagram here for what it will look like or what it does look like.
And here is our final prototype. On the left, you can see the build in its entirety with massive wires and my fancy mouse in the background. The middle contains both drawings of the prototype, the top one being the final one, with a much smaller breadboard and much more compact design. And the bottom one is our original first prototype. As you can see, it's very big. And on the right, you can see a video of us using the social distance sensor with the wrist strap that we bought. And then here's a video of it. Then here is what the prototype fully looks like when on someone's wrist. It's not perfect because this is just a prototype and not a final design, so the final design would be a lot more compact. But the wrist strap is designed just to keep it on, and it is very easy to use. It's kind of like the Ben 10 watch where you can just aim it wherever the sensor is pointing, press the button in the middle of the breadboard, and then the display will be shown on the 4-digit display. And that brings us finally to our problems and solutions. So what problems did we run into? Well, the biggest problems were how to get the code to work with everything, the size of the original prototype, getting the prototype to shut off on its own, and online class and COVID. So how we fixed these is with the code, we grinded it to no end. We used this much smaller breadboard to get the size to be much within our specifications. In order to get the battery to shut off, we just have to disconnect the battery manually since there is no way within Arduino to disconnect power. And we used a Snapchat group chat for communication when we were not in class. If we were able to do this differently and refresh the design, we would use much smaller wires for a cleaner and nicer looking build. We'd use a slightly bigger breadboard so we could fit the display on it without having all those extra wires poking out. We would use a more accurate sensor since the ultrasonic sensor is not very good for long distance sensing, and if the sound is messed with even slightly, like on a slanted surface or even a sound absorbing surface, then it'll display a really weird signal. And we would use a much bigger button because, as you saw in the video, the button that we have, you have to shove your finger in the wires to get it, and a user would definitely not feel comfortable with that. And then here are the sources we used for this project.
Thank you.
Thank you for listening.